we also did our financial maths towards the end. So please get time to go over those as well so that you are well prepared. Algebra is there throughout. Now, we are going to look at, for paper 1, this is what we should do. Solve equations, inequalities using factorization, completing the square, the quadratic formula, and substitution. We solve problems involving number patterns, sequences, and series. We determine equations, sketch, and interpret problems involving the 4 basic functions, which are linear, quadratic, hyperbolic, as well as exponential functions. We will also use differential calculus to determine the derivative from first principles and use rules of differentiation. We will sketch and interpret cubic functions. We solve problems that involve timelines and annuities, that's financial maths. We'll also solve problems that involve the probability equation as well as the counting principle. Now, we'll refer to the grade 10 to 12 CAPS document as well as the grade 12 examination guidelines. For the topics that you are not able to do, I have taken an extract from the examination guidelines so that as we practice, we know how far we can go. Now, this is the topic breakdown and the mark allocation per topic. Algebra has between 22 and 28 marks. Patterns, sequences, and series has between 22 and 28. Functions has between 32 and 38. And financial maths has between 12 and 18 marks. Differential calculus has between 32 and 38. Probability has between 12 and 18. The reason I chose calculus and functions, they are related to algebra. So if you check, if differential calculus and functions has 70 marks, algebra has 25, we already have practiced about 105 marks. And the remaining ones, we know we can get those. Let's move on and check how we can target. For us to get a minimum pass, that's a 45% pass. For functions, we must get a minimum of 15 and a minimum of 10 for differential calculus. But if we want to get a partial pass, it means for functions, we must get a minimum of 20, and also for differential calculus, we must get a minimum of 20. Moving forward, we have talked about this and we are moving forward. Those are the topics that we are going to look at. Our pre-knowledge, we know how to use functional notation, average gradient, algebra, algebraic expression, simplification, laws of exponents and sets, gradient at a point, the derivative and its meaning. The formula page, this is the formula page that we mostly use for paper 1, but remember it will be a full formula page. I just took an extract of it where we use the majority. If you check the first line, it's for algebra. We have our quadratic equation or the quadratic formula. Please, let's always refer to the formula page so that we do not write wrong formulas. We have financial maths next. We have our sequences and series, dealing with the arithmetic sequence and series there. We have our geometric sequence and series formula there. We have also our financial maths, and then we have our calculus. We have our distance formula, midpoint formula, the equation of a straight line, as well as the formula for gradient, as well as for the angle of inclination there. We move forward. Now, under algebra, we are supposed to be solving quadratic equations by completing the square will not be examined. No question will ask us to solve equation by completing the square, but you can use it if it's easier for you. Solving quadratic equations using substitution method, the K method is examinable. We know where to use the K method. We also have to solve equations using sets leading to the quadratic equation are examinable. Squaring both sides, we remember that. Solution of non-quadratic inequalities should be seen in the context of functions. So quadratic inequalities are examinable, but the ones that are not quadratic, we have to see it in the context of our functions. The nature of roots will be tested intuitively with solution of quadratic equations and in all prescribed functions. For which values of this will this have two real roots? Remember that, shifting our graphs up and down. So just to demonstrate, we are able to have, we'll be having equations like that. It's already factorized. We are solving for x. How do we get x? It's already factorized. Please do not expand and then get wrong factors. So our x here will be equal to 0, or our x will be equal to 2. You are done. It's already factorized. Answer. We get a mark there. The second one, where we need to first of all write this in standard form. So what will happen? You simplify the left-hand side and you will get x squared minus 2x plus 1 is equal to 2 minus 2x. Then you write this in standard form. It becomes x squared negative 2x. When it comes this side, it becomes a positive 2x. So it means this will give us 0. And then we have 1 minus 2. We get x squared minus 1 equal to 0. And this will now give us x minus 1. When we factorize, it's a difference of 2 squares. X plus 1 equal to 0. We get our x as 1, or our x is equal to negative 1. We are done. So you'll get a mark for writing this in standard form, factorizing, and then both values of x. We move on to the next question, where we will have our said equations. Remember what we must do. We must isolate the square root first before we can square both sides. So this becomes square root 2x. I can expand this. 2x plus 20 is equal to x minus 12 plus 10, because the negative becomes a plus on the other side. So this will now give us our answer as x minus 2. Then we are able to square both sides and then simplify. You will finish this later on. It's just a way of reminding you our inequalities. Remember, our answers should always be left as inequalities, not as our critical values. Otherwise, we are going to be losing marks unnecessarily there. We move on. For number patterns, sequences, and series, we know that the sequence of first differences of a quadratic number pattern is linear. We know that. Therefore, the knowledge of linear patterns can be tested in the context of quadratic number patterns. Remember that, it's from our examination guidelines. Recursive patterns will not be examined explicitly, and also links must be clearly established between patterns done in earlier grades. So remember, our arithmetic and geometric sequences and series, let's go back to them, and we also practice them thoroughly, including our quadratic number patterns. So I was just highlighting these so that we remember to also touch on the other topics that are examined. Remember, algebra is 25 marks. Number patterns, sequences, and series is another 25 plus minus 3 marks. So we should make sure that we score good marks there. And then we move on to our functions. So for our functions, we are interested in our x and y intercepts. We are looking at the domain and range for our functions. We have a straight line function which takes the form y is equal to mx plus c. When we are given 2 points, we have to find gradient, and then we substitute 1 point in order for us to get the equation of our straight line. Also, we can be given the equation or the graph of a straight line, and our job is to interpret. Remember, when we're given parallel lines, perpendicular lines, we must know the property. Parallel lines have equal gradients. Perpendicular lines, the product of the gradients must give us -1. So if you have the gradient of one line, you can deduce the gradient of the second line, which is perpendicular to line 1. So we look at, for our straight line, our domain is normally x, an element of real numbers, and our range y is an element of real numbers, unless the domain and the range are restricted. So if the domain is restricted, let's say between -2 and 7, it means for you to get your range, you substitute the minimum x value into the equation of the function to get the y value. You also do the maximum x value in the domain in order for you to get the maximum y value in the range. So that's how we do it. And then we have our quadratic function known as the parabola. Two forms. We have y is equal to ax plus p plus q, where we are saying the coordinates of the turning point, we deduce them as -p and q. We get it from the equation. The axis of symmetry is given by x is equal to -p. Our maximum or minimum value occurs at y is equal to q, which is our y value at the turning point. If our a is positive, we know that we'll have our minimum value. If our a is negative, we know that we'll have y as a maximum value. Our graph will be concave down like that of the parabola. This is when we are saying our a is less than 0, and if our a is greater than 0, we know that our graph will be concave up. So that's minimum, that's maximum. We must remember that. Also have axis of symmetry, axis of symmetry. We should be able to do that. The other form is known as the quadratic form, ax squared plus bx plus c. Our axis of symmetry is given by -b/2a, or we use the derivative. We equate it to 0 to get the x value at the axis of symmetry, which becomes the x value at our turning point. Now, we also have another form for the parabola, where if we are given a graph, we have x1 and x2. These are our x-intercepts. We should be able to get the form of the equation as y is equal to a x minus x1 x minus x2, where x1 and x2 are the x-intercepts that we are given, and normally we are given any other point to help us deduce the value of a. And in most cases, when you use this one, you will be given a sketch and you're supposed maybe to come up with the equation of that function. So we are reminding each other. Moving forward, we have the hyperbola. Y is equal to a over x plus p plus q. We know that our equations of the asymptotes are given by x is equal to -p and y is equal to q. We also have our line of symmetry, which is given by y is equal to x minus p plus q with a positive gradient, and the one with a negative gradient is given by that equation. Or we use y is equal to x plus c, then we substitute the point of intersection of our asymptotes. We can use that. And also the domain, its x is an element of real numbers, but x is not equal to -p, which is our vertical asymptote. Then we have the range. Y is an element of real numbers, but y is not equal to q, which is our horizontal asymptote. Now, the exponential function is given by y is equal to a times b exponent x plus p plus q, and we know that our b can be greater than 0, but our b cannot be equal to 1. we have one asymptote, y is equal to q. The domain, its x is an element of real numbers, and our y should be greater than q if a is greater than 0. Now, we also have the inverse function. I'm just taking you through the theory. Remember, for us to test whether a function is a relation or a function, remember the condition, it must pass a horizontal line test and a vertical line test. So a vertical line test is to test whether this is a function. A horizontal line test is for us to test whether a function is one-to-one. Remember, for a function to have an inverse, which is also a function, the original function has to be one-to-one. Remember? So what is the process of finding the inverse of a function? We swap x and y, and then we make y the subject of the formula on the new function. And normally, if we have the sketch of the original graph, the inverse is always a reflection of the function above the line y is equal to x. Now, for a straight line, we have y is equal to mx plus c. We interchange x and y, and we'll get y is equal to x over m minus c over m. And the domain, its x is an element of real numbers. The range, its y element of real numbers. But if we have a restricted domain, whatever is the domain becomes the range for the inverse function. Whatever was the range for the original function becomes the domain for the inverse function. Remember that? Now, to just illustrate this, if our original function is the black function, its inverse becomes the blue function. It's a reflection about the line y is equal to x. This is our line. Our dotted line is y is equal to x, which is our reflected, our line of reflection. And remember, the coordinates of the x-intercept become the coordinates of the y-intercept on the inverse function. Whatever we have as the y-intercept on the original function becomes the x-intercept. So we swap x and y on the inverse and the original function there. We move forward. Now, we have the parabola. For our parabola, for us to get the inverse, our function has to take the form y is equal to ax squared, and the inverse is given by x is equal to ay squared. When we make y the subject, it becomes plus or minus the square root. So remember, this is not a function, but if we restrict the domain, then it becomes a function, a one-to-one function. Our parabola is like this. So when we restrict the domain, it means we are dealing with only this half if our x is less than or equal to 0. And then we also have that piece if we are only restricting the domain to x greater than or equal to 0. We'll be dealing with that piece. Even if our function is concave down, we will still have the same thing. Sorry, it can't be here. It has to be that other piece on the other side. And I will illustrate this as we move along. The domain, x is greater than or equal to 0 or x is less than or equal to 0. The range will be y greater than 0 if a is greater than 0, y less than 0 if a is less than 0. We move on now. And I just want to illustrate the inverse of a quadratic function. F of x is equal to 3x squared. Remember, f of x and y, it's one thing. Where there's f of x is the same as the y value when the function is in terms of x. And then we'll get x is equal to 3y squared after interchanging. X over 3 is equal to y squared, and our y is equal to plus or minus the square root of x over 3, where x is greater than 0. Now, remember, if our x is greater than 0, if we try to sketch the inverse the inverse will be like this. And remember, when we do the vertical line test, it will not pass. So if we have plus and a minus, it means this cannot be a function. So the inverse will not be a function. Hence, we need to restrict the domain as I've illustrated there. So what do? We restrict the domain. Here we are saying x is greater or equal to 0, and we know that our inverse would look something like that. And then if we restrict the domain to x less than or equal to 0, we know that the inverse would look something like this. So it's a reflection about, so this will be negative x over square root of negative x over 3, and our x is greater than or equal to 0. Our y is less than or equal to 0. Check here. Our x is less or equal to 0. Our y is greater than or equal to 0. So that is why our domain has become the range, and our range has become the domain here. That's how it works for our inverse functions. Now, the exponential function, we are having our y is equal to b exponent x. So the inverse is given by x is equal to b exponent y, and y is equal to the log of b x. It is a function, so the inverse is a function as well. Now, the domain, it's x greater than 0, the range, it's y element of real numbers, and then the inverse of an exponential function, we have two cases. If our base is greater than 1, then our inverse will be a increasing function as well. If our base is a fraction between 0 and 1, then our function is decreasing. The inverse function is also decreasing. So you should only have two cases for inverse functions there. We have when our base is positive greater than 1, we are able to see that. If it is a fraction, then we have a decreasing function. Two cases, you are able to see our reflection line there. So we shouldn't struggle getting the inverse of an exponential function. Now, because we have to practice for tomorrow, I want us to answer question 5. I will give you 6 minutes. Yeah, I want us to practice speed. 6 minutes. Let's answer question 5 there. Welcome back. Now, I hope you are seeing it's either we'll be given a question like this for our hyperbola, or it will be sketched and we are supposed to interpret. So we have to write down the domain. Remember how we get the domain? We said x is an element of real numbers, but our x is not equal to the asymptote. So to answer this question, we will get our domain as x is an element of real numbers, x not equal to 1. So if you do not write x not equal to 1, you will not get this mark because they have to go together for 1 mark. So it's 1 mark. Write down the equations of the asymptotes. So our asymptotes, you are able to see there our q is equal to 0, which means our y asymptote is given by y is equal to 0. X minus 1 should be equal to 0, and this will give our x as 1. That's our vertical asymptote, and our horizontal asymptote is given by y is equal to 0. We have our 2 marks. We need to sketch the graph. In order for us to sketch the graph, we need our x-intercept as well as our y-intercept. Also, remember, if our a is negative, we know that our graph will be, we have two conditions. If our a here is negative, which means our graph is going to be in quadrant 2 and quadrant 4. Remember this, a less than 0, our graph should be in those quadrants, and we get those quadrants using our asymptotes, and we are able to sketch our graph. Our y-intercept, f of 0, where there's 0, where there's x, you put 0, so it becomes positive 1. So 0 and 1 is our y-intercept, so we'll get that. We'll not have an x-intercept because we are having 0 is equal to 1, which is undefined, so there is no x-intercept because our x-axis is an asymptote, so our graph will not intersect the x-axis. Hence, we'll have the two arms of our hyperbola. Remember, you must have two arms, and then we will get a mark for the y-intercept, a mark for the asymptotes, and the shape in the correct quadrants. We get our 3 marks there. For which values of x will x times the first derivative of x be greater than or equal to 0? Please note, this is an interpretation question. You must know what it means. So remember, from our laws of derivatives, the derivative of 1 over x, if I have f of x, this becomes negative 1 over x squared. That is the derivative. So you must know that concept. If you check now, this is our f of x in this case, it's negative 1 over x, which means this becomes positive. So how do you get a positive? It's when you are multiplying, our x has to be positive and this has to be positive for us to get a positive. Our derivative can never be negative, so we are only looking at the region where x is greater than or equal to 0, but our x cannot be equal to 1 because when x is equal to 1, it's our asymptote. You must remember that condition, x greater than or equal to 0, x not equal to 1, we get our 2 marks. We have 8 marks there. Remember, we are fighting for 20 to get a bachelor, so we still can get another 12 from the remaining 27 marks. So it's possible we can do this. Let's move on. Now, here is another question that I would want us to quickly answer. I will give you 5 minutes to answer this one. Welcome back. I want us to practice time so that in questions where we can move faster, we should move faster. And then in questions that will need us to read the question more than 3 times, at least we will have enough time, because remember, in our exam, it's 1.2 minutes per mark. Now, let's read the information. In the diagram below, A and B are the x-intercepts of the graph of f of x, which is given by x squared minus 2x minus 3. A straight line G through A cuts F at C with coordinates 4 and 5, and the y-axis at 0 and 1. M is the point on F, and N is a point on G, such that MN is parallel to the y-axis. MN cuts the x-axis at T. We must read that information before we answer the question, so that if there's information that we need to add to the diagram to make things clear, it becomes easier for us to see. Now, so we know that the coordinates here, we are only seeing one. We know that this is 0 and 1. It will help you to see. It says, show that the graph of g of x is x plus 1. Now, already you know that the value of c there on the equation y is equal to mx plus c, we are able to deduce that our c there will be 1. Our job is to show that the gradient is 1. How do you do that? You have 2 points, the y-intercept and point C, to give us the gradient of g of x. And we are able to move on from there. So using that, we find the gradient using the coordinates. Remember, we said this is 0 and 1. So it helps you to see what can help you. Gradient formula, the gradient of that line AC will be given by the y coordinate is 5, 1, 4 minus 0, and this will give the gradient of 1. We have the value of our gradient. We have the value of our C as 1. We are done. Moving forward, we have to calculate the coordinates of A and B. If you look at A and B, A is the x-intercept and B is also the second x-intercept. So how do we get the intercept? We let our f of x to be 0 or our y is 0, and we get x squared minus that is equal to 0, and then we factorize, and we get our x as negative 1 and the other x as positive 3. From there on, we get A is on the left, it's negative 1 and 0, B is 3 and 0. Remember, the question was specific. Calculate the coordinates. So you should leave your answer as coordinates. So for substituting 0, you get both x values, and then our coordinates of A and B, we get 3 marks there. Determine the range of f. For us to get the range, remember, our graph is concave up, which means we want the coordinates of the turning point to help us get our y value at the turning point. So how do we do that? I have the x-intercept. I can either use the x-intercept at A plus the x-intercept at B divided by 2. This will give our x as 1. Or I use negative b over 2a because I have the equation and I'll get my x as 1. Or I find the first derivative equated to 0 to get my x at the turning point, and I'll get my x as 1. You can use any of the 3 methods there to help us get our x value at the turning point. After getting the x at the turning point, we substitute it into the original equation to give us the y value at the turning point, and we get our y value as negative 4. And then we will get our answer as y is greater than or equal to negative 4, or you can give it in interval notation. We get our 3 marks again. Now, in the interest of time, I will do 6.41 with you, 6.42 with you, and the equation of the tangent drawn to F parallel to G. You can see this requires us to come back to calculus, hence I will do it with you. For which values of k will f of x and h of x given as that not intersect? Our nature of roots as well come into play, knowing what does it mean not to intersect. Let's quickly go over those questions together. I will be giving you the answers and explaining as we move along. So to determine the length of OT, OT is the distance from the y-axis to the point T. How do we get that one? Remember, mn is the distance between f of x and g of x. It is 6 units. So we have to show that. So we subtract the two functions. So we subtract f of g of x from f of x, and that should give us 6 as the distance mn, and it will give us x squared minus 3x minus 4. We equate that to the distance, which is 6, and then from there on we get our x as 5 or our x as negative 2. You can see it's standard form, factorize, get the solutions. But you are able to see that we are looking at the negative side of our x values, hence we will not take our x as 5 on the negative side, so our x is negative 2. So the distance, if this is negative 2, it means our x value along the line mn, it's negative 2, and that point T is at that point, so the coordinates here will be negative 2 and 0 like that. And we are saying the distance OT is 2 units in the negative direction. So because it's a distance, we ignore the negative sign because distance is a scalar quantity, it has magnitude. Now we move on to 6.42. Hence write down the coordinates of n. The coordinates of n. For you to get the coordinates of n, we know that along the line mn, our x value here, it will be negative 2 and f of negative 2. That's how we get coordinates. N here, it will be negative 2 and g of negative 2. So that's how we get the coordinates there. So we will say our x, our function for g, we got it as x plus 1. We substitute negative 2 plus 1 and we get negative 1, which means our x value there, it's negative 2, and our y value there, it's negative 1. We move on to the next question, 6.5. Determine the equation of the tangent to F drawn parallel to G. So, we want to find the equation of the tangent of F drawn parallel to G. And that question is 5 marks. So, if it's parallel to G, how do we get? We know that we find the first derivative. After finding the first derivative, it gives us the gradient function. The gradient at that point should be equal to 1 because the gradient of the function g of x is 1. So we equate the first derivative to the gradient, and then we get our gradient as 3 over our x value when the gradient is 1 as 3 over 2. So from there on, we are able to find our function. When our x is 3 over 2, we substitute it to the original function, which is f of x. We evaluate f of 3 over 2. Where there's x, we substitute with 3 over 2, and this will give our y value as negative 15 over 4. That becomes our y value. Our gradient, it's 1. We substitute c, and we get our equation as y is equal to x minus 21 over 4. And then from there on, we have the equation of the tangent parallel to that point. Are we happy with that? So it's 5 marks. We equate to the gradient. We get our x value. After getting our x value, we evaluate the point of contact. Then we get our value of c. And then from there on, we have our equation. Once we get the value of c, we get our equation, and then we get our 5 marks there. For which values of k will f of x equal to x squared minus 2x minus 3 and h of x equal to x plus k not intersect? So when will they not intersect? It's when our k is less than negative 21 over 4. Remember, if we are saying this is parallel, it means we are somewhere here. We are having the tangent, and this is the point of contact. So once our y, we are looking at the y-intercept. So our y-intercept here will be 0 and negative 21 over 4. So once our y-intercept is less than negative 21 over 4, it means our line is still parallel, but it will no longer intersect our graph there, and we get our 1 mark. We move forward. We look at our inverse functions. This one, I'll give you time to play around with it. I'll give you 5 minutes to answer that question number 4. Welcome. G of x, which is given by a, 1 over 3 exponent x plus 7, which passes through the point E with coordinates -2 and 10. We are supposed to calculate the value of a. How do we calculate the value of a? Now, remember we are given a point, so our job is to use this point to help us get a, because we have the value of x, we have got the value of g of x. So, to answer this question, we are going to use our g of x is given by a 1 over 3 exponent x plus 7. So to answer this question, we are going to say g, we are given the coordinates of -2, it's given by a 1 over 3 exponent -2 plus 7, and our g of -2 is 10. 10 plus, if we put 10 minus 7, it will give us 3 is equal to this, will give us 9a. We get our a as 1 over 3. So for substituting the coordinates, simplifying, getting the value of a. Our next question, we're supposed to write down the, let me go back quickly. Right. I moved very fast. Calculate the coordinates of the y-intercept. So for us to calculate the coordinates of the y-intercept, I will work it here because we need to see the questions. We said our a here, we got it as 1 over 3. And we are saying our g of x is going to be 1 over 3 exponent x plus 7. We need to calculate the coordinates of the y-intercept. For us to get the y-intercept, we know that we are going to have g, our y-intercept, our x is 0, g of 0 becomes 1 over 3 exponent 0 plus 7. And this will give our g of 0 as, so it becomes 1 over 3 plus 7, it will give us 7 and 1 over 3. And we know that it will give us 7 times 3, 21. So this will give us 22 over 3, which means the y-intercept will be 0 and 22 over 3. We get our 2 marks. Method, answer. So we are given h of x is equal to 1 over 3 exponent x. So we want to describe the transformation. Now, I want us to look at this. G of x, we got it as 1 over 3 exponent x plus 7. Bases are the same, so I can write my g of x as 1 over 3 exponent x plus 1 plus 7. Now, want to describe the transformation. We are moving from this to get that. So, as you can see, this is going to be plus 1. So, we are moving this function 1 unit to the right and 7 units down, because I've moved from plus 1 to that, so it means it's plus 1 minus 1. If it's a minus, we are moving to the right, 1 unit to the right, 7 units down, because I'm moving from 7 plus 7 to 0, because my horizontal asymptote is now y is equal to 0, so it's 7 units down. So please, 1 unit, you must say to the left or to the right, 7 units up or down for you to get full marks. The equation of the inverse of h, so we are saying our function now, it's y is equal to 1 over 3 exponent x, interchange x and y, we get 1 over 3 exponent y. which means our y is equal to the logarithm to the base of 1 over 3x. Then interchange x and y, the equation will get your 2 marks. So we must be able to get these marks. Moving forward, we are looking at differential calculus now. According to our examination guidelines, the notation that we are supposed to use, if our function is f of x, g of x, k of x, the derivative becomes f dash, g dash, k dash of x. Or we use dx, it means we are doing the derivative with respect to x, or we use dy dx, or we use y prime. Now, this is from our examination guidelines. In respect of cubic functions, candidates are expected to be able to determine the equation of a cubic function from a given graph, discuss the nature of stationary points, including local maximum, local minimum, and points of inflection, apply the knowledge of transformations on a given function to obtain its image. This can also be asked under functions. Now, we move on. Candidates are expected to be able to draw and interpret graphs of a derivative function and its original function as well. Candidates must know the formula for the surface area and volume of right prisms. These formulae will not be provided in the formula sheet. If the optimization question is based on surface area and or volume of a cone, sphere, or pyramid, a list of relevant formulae will be provided in the question. Candidates will be expected to select the correct formula from the list. Please be aware, you must know which formula to use. It will be provided, but you must know which one to use. And we know that surface area and volume will be examined in the context of optimization. Now, let's move on. So, we must know the definition of the derivative from first principles. I will not illustrate that. We know that it's given on the formula page. It is the limit of h tending to 0 of f of x plus h minus f of x over h. Please be careful here. You will be penalized if your notation is wrong. So please, let's make sure that we practice the correct notation. We put the equal sign in the correct place. Our limit h tending to 0 must be under the word limit, and then we have our fraction f of x plus h minus f of x over h. It's different. It must be. You mustn't mix this. Others write it wrongly and it becomes lim. The common mistakes that we make, f of x plus h minus h f of x. Then you will find the equal sign there, and then you will find h tending to 0 over h like that. So please, let's not mix up. We write it the correct way. We compute and simplify f of x plus h separately, and then we substitute the expression of f of x plus h and into the definition, and then we simplify. We avoid substituting h is equal to 0, but we check what happens to the expression as h becomes smaller and smaller. Now, the notation, we determine the derivative of a function. We also say that we differentiate the function. The process is called differentiation, and what the result that we get is called the derivative or the gradient function. Now, the notation, if we are given our function in terms of f of x, the derivative is that. So if we are given our function in terms of x and we are finding the derivative with respect to x, it's y is equal to a exponent x plus that. The derivative becomes dy dx. D of x expression, we do not write dx when we apply the rules. And then we also find d dx of the expression. The rules, we know them. Below, our exponent multiplies the coefficient and our exponent is reduced by 1, and we are able to get the derivative there. And we must be able to do the derivatives of our composite functions where we have different exponents, so you differentiate each one as it comes. 6x cubed plus x to the exponent 6, so the derivative becomes 18x squared plus 6x exponent 5. Now, a constant, its derivative is 0. The derivative is 0. If we are finding the derivative with respect to x, if I have a number 5, its derivative is 0 with respect to x. Here is an example. We are given, this question is extracted from the November 2018 question number 8. We are supposed to find the derivative from first principles. So, for us to find the derivative, remember, we said we evaluate f of x plus h, which becomes x plus h squared minus 5. When we simplify this, it will give us x squared plus 2xh plus h squared minus 5. So we want the derivative f dash of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So I will substitute the limit as h tends to 0. This will be x squared plus 2xh minus 5 minus x squared minus 5, all this over h. X squared and x squared will go, 5 and 5 will go. We are now left with 2, the limit as h approaches 0 of 2xh over h. H and h goes, and this will give us our answer. Oh, I forgot to write plus h squared here. Plus h squared. My apologies. So this h can cancel that h. In our next step, it's our limit. H approaching 0. H is a common factor. I will have 2x plus h over h. This h and that h will go, and then we will get our answer as 2x. That's how we get our 2x. Then we have that one. We have our function in terms of y is equal to 3x squared. So for us to do the derivative, we apply the rules. Dy dx will be equal to 3 times 3 will give us 9x squared plus 12x plus 1. So for each of these derivatives, you get a mark. And then the next one, we are supposed to, I will start it here. If you check, y is a common factor, I can write that as y is equal to x minus 1 is equal to, I can also factorize 2, and I can factorize 2x, sorry. I'll remain with 2x is equal to x minus 1. From there on, I'm able to get y will be equal to 2x, x minus 1, all this over x minus 1, and these are like terms, they will cancel each other, then I'll have y is equal to 2x. After simplifying, then I can apply the rules. Dy dx will be equal to 2, and then we get our marks there. Please, let's get these marks. Let's not leave them. Remember, if we are having sets And square roots, remember to apply your laws of exponents. Square root of x is the same as x exponent half. Cube root of x is the same as x exponent 1 over 3. So we should apply those exponents, and then we only after simplifying can we then apply the rules of differentiation. We move forward. The equation of a tangent, we know that a straight line that touches a curve at only one point is called a tangent of a curve. So it's given by y is equal to mx plus c, and the tangent to a point on the curve is a straight line that touches the curve at that single point and has exactly the same gradient as the curve at that particular point. M is the gradient. And how do we get the gradient? It is the first derivative at x is equal to a. And x1 and y1, these are the coordinates of the point on the line. And then we use the equation of a straight line. So to find the y value, whatever we get as our x value, we substitute it back into the original function to get the corresponding y value at that point. And then we use the equation of a straight line to get the equation of the tangent. Now, we also have to sketch cubic polynomials. Remember our factor theorem, where we are saying if f of a is equal to 0, then if we are given a cubic polynomial, we know our factor theorem, then it means x minus a is a factor to the polynomial. From there on, we can now use our methods of division. We can use synthetic division, long division, or we can use inspection to get the other points. And we know that our value of a determines the shape. If our a is greater than 0, then we have an increasing function. If our a is less than 0, we have a decreasing function. And then the intercepts, we use our factor theorem and get the first factor. We can now use long division, synthetic division, or inspection. We can factorize if we can, or use the quadratic formula. We solve to get our x values. Number 3, to find the x values at the turning point, we find the first derivative, we equate it to 0, then we solve for x. Whatever we get as our x values there, we substitute them into the original function to get the corresponding y values at the turning points. For us to get the point of inflection, we find the second derivative, we equate it to 0, and we solve. Here is an example. X cubed minus x squared minus 8x plus 12 is the function. Our a, the coefficient of x cubed there, is positive. Hence, we are saying a is greater than 0. The shape will be an increasing function. We are able to see that our a is greater than 0. It will be an increasing function. And then for us to get our x-intercept, we use a factor theorem. It's not a factor, then we get 2 as a factor. Then from there, we can either use long division or inspection to get the other factors. So I've already factorized it. I'll get x squared plus x minus 6 multiplied by x minus 2. So from there on, I'm able to factorize, and I see that x equal to 2 is a repeated root. And I know that the moment I have this scenario, I know that x equals to 2 is both a turning point as well as the x-intercept. And then from there on, I am able to find the turning points, find the first derivative, equate it to 0, then solve, and I will get the factors, or I can use the quadratic formula there, and this will give me my x as 2 or my x as negative 4 over 3. To get the corresponding y values at the turning points, I'll substitute x equals to 2, of which I know it will give me 0. I'll substitute negative 4 over 3, and it will give me 500 over 27 as the y value. And from there, my point of inflection, I'll do the second derivative, and it will give me my x as 1 over 3. That's my point of inflection. I take 1 over 3, I substitute it into the original function, and it will give me 250 over 27. Those are the coordinates of my point of inflection. From there on, I have my x-intercepts, I have my turning points, I also have my point of inflection. I'm now able to sketch my graph, and it's an increasing function. So I will have all my points there. I sketch the graph. Now, here is a question, but because of time, it's not on our side. I will go through it with you so that we remind each other of these concepts and apply them practically. We are given that the graph of f of x is 2x squared, 2x cubed, 2x cubed there, 2x cubed plus 3x squared minus 12x, and it's sketched below. And we are told A and B are the turning points of F. C has coordinates 2 and 4, is a point on F. Determine the coordinates of A and B. Remember, A and B are our turning points. How do we get our turning points? We find the first derivative of f of x, and we get 6x squared plus 6x minus 12. We equate it to 0. And then we factorize, and we get our x values as those two. And then we also get our y values. Then we are able to get our coordinates of A as negative 2 and 20, the coordinates of B as 1 and negative 7. We get our 5 marks. For which values of x will f be concave up? So concavity, we are looking at our point of inflection, and it's easy for us to get our point of inflection. We have our x values at the turning points. We can either use negative 2 plus 1, we divide that by 2, it will give us the point of inflection, or we find the second derivative. First derivative, second derivative, we equate it to 0, or we say it's greater than 0. We are able to get our x as negative 1 over 2. So for any values that are greater than, remember, our x is negative half, will be somewhere there. Concavity changes at this point. From here up to that point, our graph is concave down, and then it is concave up for x greater than negative 1 over 2. So we find second derivative greater than 0, knowing the condition, and then getting our x is greater than negative half will give us that mark. The next one, determine the equation of the tangent of f at C with coordinates 2 and 4. So remember, we need the gradient. We have the coordinates of the point for us to get the equation of a straight line. So we found our first derivative. At point C, our x is 2, so we'll substitute 2 there, and we get our gradient as 24. So it means our gradient is 24, and we use the equation of a straight line, or we can use y is equal to mx plus c, and we get our equation as y is equal to 24x minus 44. So that is the equation of the tangent at point C. So the examiners can just change this part and not give you the coordinates of C, which means they can use parallel to whichever line then, or where the gradient is 7, so you must know the steps. find the first derivative. If you are given the value of the gradient, you equate it, you get the x value. Once you get the x value, you substitute it into the original function so that you get the corresponding y value. And then you use the gradient and the coordinates of the point to get the equation of the straight line. These are easy marks. Let's get them. Moving forward, we are given the graph. So sometimes also we'll be asked to interpret the question. We are given that the graph of g of x is x cubed plus bx squared plus cx plus d is sketched below. The graph of g intersects the x-axis at -5 and 0, and at p, the y-axis is 0 and 20. P and R are the turning points. We have to show that the value of B, C, and D are those. So D, it's our y-intercept 0 and 20. We are able to get that one. But how do we get the remaining ones? So our steps will be already. We know that we can use, just like our parabola, our g of x can be given as a x minus x1, x minus x2, x minus x3, if we are given the intercepts. You see that we have a repeated root, so which means P is both a turning point as well as the x-intercept. So we call that one x1, and we substitute -5, and our equation becomes that. When our x is 0, our y is 20, we substitute the coordinates of that point and we get 5x squared. Our job is to solve for x. So we get our x1 as 2. So the coordinates at point P will be 2 and 0. Those are the coordinates at point P. So from there on, we are able to get our g of x as that. How do we get it? We substitute x plus 5 squared, and then it will give us the value as, so you multiply this first and then it will take you back there. So you are able to see that your A is 1, your B is 1, your C is -16, and your D is going to be 20 when you compare the original equation and what you are getting after doing the substitutions there. We have to calculate the coordinates of P and R. What do you do? P is a turning point, R is a turning point. So remember, first derivative equate to 0, solve for x. We are getting those, and then we substitute back into the original function. So P, as I indicated, it's 2 and 0. That one becomes that. Derivative equate to 0, get your x values and get your corresponding y values there. Then we are able to get those 5 marks. We move on. Is the graph concave up or concave down at the point 0 and 20? How do you know? We know. We find the first derivative and then we substitute 0 there, it will give us +2. So because our g of x, our g dash of x, g dash dash of x, it is greater than 0, therefore it is concave up. Now, we use that, we get our point of inflection as -1/3. That's where concavity changes, and therefore it's concave up because our point of inflection is -1/3 and 0 is on the other side. It will give us concave up. Now, here is another interesting question where you are asked to interpret and sketch a graph. Remember, we are told that if g of x is a cubic function with g of 3 equals to the first derivative of at x equals to 3 is equal to 0. So it follows that we have a point with coordinates 3 and 0, which is g of 3 equals to 0. We know that this is an x-intercept. 3, 0. Because of the g dash equals to 0, it means this is a turning point as well. Now, at 3, 0, it's also a turning point. G of 0 equals to 27. We know that 0 and 27, this is our y-intercept. We also know that the second derivative, g dash dash, is greater than 0 when x is less than 0, and g dash of x, g of x is less than 0 when x is greater than 3. We know that this becomes a point of inflection as well. So we know that 3, 0 is also a point of inflection. So to sketch the graph, we are able to see that it should look like that, because we have a y-intercept at 0 and 27. We also have our point of inflection and a stationary point at x is equal to 3. And we also have concavity changes there. So that is why we are saying the graph would look like that. So we must know all these conditions. Moving forward, we have optimization, but I'm seeing time is not on our side. We have direct and indirect application, where we are supposed to find, or when we are given the objective function, and when we are supposed to find the objective function before we can apply it. So, moving forward, this application occurs for our word problems, shapes, areas, volumes, perimeters, application to graphs. We also have rates of change, which include motion. So we must practice these as well. There are a lot of them. I had chosen this one, where we are given that the number of molecules of a certain drug in the bloodstream T hours after it has been taken is represented below. And we are told that the function is mt is equal to our t negative t cubed plus 3t squared plus 72t between 0 and 10 hours. We have to determine the number of molecules of the drug in the bloodstream 3 hours after the drug was taken. So remember, 3 hours, it means our time is 3. So where there is t there, we just substitute 3 and it will give us an answer of, so we substitute and it will give us 216 molecules. So you substitute your 3 and then you get 216 molecules. 10.2, we are supposed to determine the rate at which the number of molecules of the drug in the bloodstream is changing at exactly 2 hours after the drug was taken. So rate, we know that we do the first derivative. After getting the first derivative, we substitute the time and it will give us 72 molecules per hour. It's a rate of change. So it will be 72 molecules per hour. It's a rate. If it was distance, it will be distance, and time, it will be meters per hour, per second, per minute, depending on the units that we are using. 10.3, we are supposed to find how many hours after taking the drug will the rate at which the number of molecules of the drug in the bloodstream is changing be at a maximum. So at a maximum, we find the first derivative and we find the second derivative, our point of inflection. We equate it to 0, then solve for t. So the time will be after an hour. Now, it's the rate that is changing but if they'd asked us at what time will we have the maximum molecules in the bloodstream, you'll just do the first derivative, equate it to 0, then you solve for t. That's how you get it. So please, let's practice these questions, areas and volumes as well. We practice them. So in summary, the function notation must be used to solve problems involving sketching, interpretation of functions, and derivatives. Now, we solve and interpret problems involving number patterns, sequences, and series. Let's revise everything. We use the correct notation to get the derivative from first principles, and we're using the rules of the given expressions. I have emphasized this. We use differential calculus to determine the equation of a tangent and coordinates of point of contact and to sketch cubic functions. We solve problems involving financial mathematics and probability. That is the one that we did not touch, but please, let's practice and make sure we make it. I thank you and good luck for paper 1. All the best tomorrow. We meet again tomorrow in the afternoon to revise for paper 2.